has to do with infinite type surfaces. And this is at an early stage, so I'm just sort of working out what these objects look like. And it has to do with geodesic laminations on infinite type surfaces. There's an extensive theory of laminations for finite type surfaces. And but there's not much for infinite type surfaces, except for the things that could transfer over from finite type to infinite type. So today's talk is rather preliminary, but it also is going to underscore some of the real differences between finite topological type and infinite topological type. And one thing I should say as maybe a advertisement for infinite type surfaces, you could take this as the good advertisement or the bad advertisement. If you just ask for how many topologically infinite type surfaces are there, just topological type, it turns out there are uncountably many. So that's sort of interesting because, of course, for finite type surfaces, there's genus and number of poles tells you everything. So it's countable. Anyway, having said that, let me begin. That's the official time, right? I'll put this away. Okay, so the first thing, so this is all about the hyperbolic plane. So H is going to be the hyperbolic plane. And G of H is the space of geodesics. In H. So what do I mean by it? So space, well, a geodesic, these are unoriented. So a geodesic is determined by its endpoints on the boundary. Okay. So this can be identified with, and this is how we put the topology on the space of geodesics. 2 points on the boundary, take away the diagonal, and since they're unoriented, mod out by the Z2 action that takes one endpoint to the other. Switches. So that puts a topology on the space of geodesics. And so for instance, this sequence of geodesics converges to this dotted geodesic here. These endpoints are converging to the inputs over here. So if we have does it get dark here? Can you see? Can you see over here? So if we have a hyperbolic surface, S a hyperbolic surface, any type, well, if we think of S as the hyperbolic plane mod a torsion-free discrete subgroup of isometries, then we could define the space of geodesics on the hyperbolic surface as, well, you take the space of geodesics on H and you mod out by the action of the group on the geodesics. Okay? This is a highly nasty space, Hausdorff, everything. But in any event, there's a space of geodesics associated to the hyperbolic surface. So maybe just to give you a feel for what this is, So remark, gamma n converges to gamma on S if, so these are geodesics on S, and we're saying they converge in this topology if there exists lifts, gamma tilde and gamma n tilde of gamma and gamma n respectively, so that okay? So I'm just translating what this is upstairs. So if you could find a lift of this and lifts of this that converge in this guy, and these are easy to understand, because this is just endpoints converging to endpoints, then we say that the gamma n converges to gamma n. Okay. So I won't assume that people know what a geodesic lamination is or anything, so I'll define a lot of these objects. So definition of geodesic lamination, and I'm just going to say lamination for the purposes of this talk. Is the union, disjoint union, of simple geodesics which forms a closed set. Or maybe I should say whose union forms a closed set. In S. So for example, there's a rich set of examples. The simplest example is simple closed geodesic on S, or a finite union of disjoint closed geodesics. But then you can get more interesting, and there are lots of much more interesting lamination. But let me just give you one picture, give you the idea of maybe something interesting going on. This is a pair of pants. Okay? So a pair of pants is a hyperbolic surface with geodesic boundary, and these are the geodesic boundary curves for this pair of pants. And I want to look at this curve. It's a simple closed geodesic. This curve, and this one, which spirals into this and spirals into this. That's gamma. Okay? That's a lamination. Okay? Forms a closed set made up of disjoint union of simple geodesics. And the topology on this space is interesting. On this lamination is interesting. So let me back up. We have this lamination. It's a union of geodesics. Okay. Well, the space of geodesics has a topology. Therefore, you can put the subspace topology on here, so the lamination has a topology. Okay? Well, that topology is the same topology as the leaf space topology, in the sense of if you take each one of these curves and collapse them to a point and look at the quotient topology of that. So in this example, if you do that, so leaf space of this lamination, let me call this L. Well, what is it? This is a good exercise, actually. Well, it's a finite topology. Like there's 3 points. And I'll let you work it out. Of course, here's one of the open sets. This is the one that, this point is the one that corresponds to gamma. This one to beta. This one to beta prime. And gamma is isolated in this topology. And any open set that contains beta is also forced to contain gamma. And the same for beta prime. So I'll leave this to you if you want to play with this. So there are, how many sets, open sets are there? 1, 2, 3, 4, and the empty set. 5 open sets in this topology. Okay. Highly non-Hausdorff. Even on this, at the lamination level. I mean, I said that the space of geodesics is highly non-Hausdorff and an ugly topology, but, or ugly maybe not the right word, it depends on the observer. But even when you go down to the set of to a lamination, you ask for the subspace topology in there. Still, could have some, say from the other point of view, rich things that happen, rich perspective. Not okay, so that's a geodesic lamination. Here's a couple of examples. Each of the geodesics are called the leaves of the lamination. Okay, so I'll just these are leaves. And they're either the closed leaves, which are, in this example, beta prime and beta. And then gamma, we'll call it open leaf. Okay, so when you have a lamination, it's made up of leaves. The leaves are either closed or open. So, one thing that happens for finite area surfaces is, well, you can, let me back up. You can ask this question. Suppose I have a geodesic lamination, and gives me this closed set, okay, on the surface. Is that the only way, is that the only geodesic lamination that gives you that closed set? In other words, does knowing that you have a geodesic lamination and the closed set determine the actual leaves of the lamination? That's another way of saying it. Or is there another way of writing that same closed set in terms of a geodesic lamination? So if the surface has infinite area, well, back up. If the surface is, say, here's an example where if the surface is the hyperbolic plane, here's a lamination. Well, there's lots of laminations that you can draw. Just the lamination being all the geodesic that sort of come down, just converge. Boundary point, if you like. Okay? Including this guy. This is uncountedly many of these. It's a closed set. Okay? And of course, there's more than one way of doing this. Okay? So this tells you that it's not unique, you're going to have to put some extra conditions on there. And in fact, the right words are, if the surface is of the second kind. In other words, if the surface, when you realize as the hyperbolic plane mod the Fuchsian group, if that Fuchsian group has action on the boundary, which has intervals of discontinuity, then things like this can be constructed, and you don't have uniqueness of geodesic lamination. But if the group is of the first kind, you do. Yeah.
So the point is that on the boundary we have a lot of points and we have different choices as how to match them up?
No. It's just, here's the geodesic lamination. All the leaves are these open geodesics, right? That's one way of writing down this closed set. Here's another way. Instead of doing this, I could have done this.
Oh, just the subset of the hyperbolic plane, is it?
Mm-hmm.
Yeah, it's just the closed set is just a subset of the hyperbolic plane, right? Because the closed set is in the surface. It's the union of the leaves. So what is true is that if our hyperbolic surface S is of the first kind, and I'll come back to this and be more explicit about what that means when I'm going to talk about Fuchsian groups. But just suffice it to say now for the people who know, this group is acting on the circle, on the boundary of the hyperbolic plane, and its limit set is all of the hyperbolic, all of that boundary. And that's what first kind means. So if S is of that form, then how do I write this? There exists then a closed set in S, which is a geodesic lamination. Can be written in only one way. Can be written as a geodesic lamination in only one way. Okay, so this is well known for finite area objects. And the point here is that that same argument works, whether the surface is finite area or infinite area. The important thing, if you look at the actual proof, it's essentially the same. The important thing is that the action of the group be of the first kind. You don't have these open intervals on the boundary where you can play this kind of game. And in fact, let me just give you the idea. The idea is if you have a closed set on the surface and it has these, so if L, so right here, if L is a lamination and it can be written as here's the leaves, the gammas. Gamma A maybe, where A is in some index set. And as the union of some other leaves, A or B, B is in the index set. So that's what it would mean if you had two different ways of writing that closed set as geodesic laminations. But then, if the laminations are different, then one of the leaves has to be different than one of the leaves here. So what you'd see is, you'd see a lift up in the hyperbolic plane. This is taking place in the surface. You'd see a lift on the hyperbolic plane of maybe one of these gammas. And then you'd see a lift of one of these betas that crosses it transversely. And the point is, while all of these points have to still be in that lamination, that closed set. So that means that these gammas, these leaves, there's a whole bunch of these leaves that sort of go through like this when you're close to this intersection point. Well, that means that this is thick. But if it's thick, I mean, it could come back to, they could all focus to a point on the boundary on one side, but they can't on both. So on one of the sides, there's sort of an interval here in which the leaves are hitting the boundary of St. Gamma. But that's going to violate, that's easy to show that it violates the action of the grouping of the first kind. Because you use double density of the hyperbolic elements, and you could show there's no way you can move this set that's hitting the boundary so that it intersects itself. But that's a contradiction because these are supposed to project to simple guys. Okay? So no finite area argument here, it's just the first kind of. Okay? And let me say, there are lots of surfaces of infinite type of the first kind. That's why I'm emphasizing this point. All right. Okay, good. So there's a particular kind of lamination I want to focus on. That's what this talk is about. And these are called DCL-laminations. I'll explain that in a moment. But to explain that, I have to give you another definition. So we said our lamination has a topology, right? Coming from the leaf. These are all equivalent to leaf space topology, or the topology is a subspace of the space of geodesics. Our lamination has a topology. Well, if it has a topology, the leaves, which are the points of this topological space, which is the leaf space, the leaves could be isolated. Okay? So I'm going to state that in a little different way than just saying what I just said, because it's more hands-on to say it this way. This definition, this is Cassie Blyver's. That's the first place I saw this definition of isolated, but this is cool. Okay, so L is the lamination. On S. A leaf, gamma, is said to be isolated. If for any point x on the leaf, gamma, there exists an open set, an open neighborhood, u sub x of x. So this u sub x is an open neighborhood ux in the surface S. So that you want this picture to, what should it mean to be isolated? It should be that you pick a point x, and there should be a neighborhood. Here's the surface S. There should be a neighborhood in which no piece of the lamination comes through here. Okay? So one way to say that is, so I'm saying this in the topological setup, the pair of ux with ux intersected L. So ux intersected L is this. And this is ux. That should be as a pair. as a topological pair. Just the same as unit disk and a diameter. Right, so you know what this means. This means that there's a topological map that takes this neighborhood for the unit disk and takes this intersection to this. Okay. This is equivalent to, if you want to wind this is equivalent to leaf in the leaf space being isolated. In fact, maybe I'll write that down. So, so gamma in L is isolated. If and only if a lift gamma tilde of gamma to H in the, okay, so whenever you have a lamination on the surface, you could lift the lamination, the whole thing, up to the hyperbolic plane, you still get a lamination. Okay. And so that's what I mean by this. So this is the lifted lamination to the hyperbolic plane. And what you should see is that if gamma was isolated downstairs, then there should be a lift of it in the lifted lamination, which is isolated. So is isolated. So a lift of gamma tilde is isolated in the space of geodesics. Okay, so typically you'll see something like this. Here's your surface. I'm not going to draw something closed. I'm not even going to draw something finite area. Because this is all about infinite type, right? So I'll do this. It's called the fluid surface. It's called the fluid surface. Okay. So typically, you might have some lamination on here. And now when you lift it, and you see all these leaves upstairs in the hyperbolic plane, and this lifted gamma tilde has to be isolated among those lifts. Okay, so so that's what it means to be isolated. So let me digress. Maybe this whole thing is a digression, but let me digress from this discussion and just remind you of something that maybe you saw a long time ago, maybe you didn't, and this is called the Cantor-Bendixson derivative. So what is it? Well, all it is you could define this for any topological space. You have a topological space, its derived set, fancy words, the Cantor-Bendixson derivative, is the topological space, which is take that topological space you started with and throw out all the isolated points. You could iterate this. Okay? You could iterate this in any fashion you like, in the sense that We usually say iterating, we mean, what do we mean? We mean through the natural numbers. But you could iterate this through the ordinals. Okay, so that's what I want to just mention here. So let me just say, and I'll say this in terms of laminations, the lamination being the topological space, but this discussion is all about just topological spaces. So the L lamination. Then DL is the leaves. Oh, let me write it this way. It's L minus the isolated leaves. Okay. And note, this is a closed set, so this is a sublamination of the original lamination. And I use the fancy word using transfinite induction. You can define so for beta, a success for beta, an ordinal. The beta plus the first derivative of L is to take the beta derivative of L. It's the obvious thing. Take the derivative of that. If you don't like the words ordinal and stuff, just think of the integers, the positive integers for this discussion. But it is more general than that, and that is useful. So that's if, so this is defining it for a success, this is called a successor ordinal. If there's one other kind of ordinal, that's called a limit ordinal. For a limit ordinal, you do the obvious thing. So if beta is a limit ordinal, maybe this isn't so obvious. Then the beta derivative. So you're assuming you know the derivatives before beta. Then the beta derivative is the intersection of all the derivatives before. Again, it came before beta.
Is that obviously closed?
Sorry?
Is that obviously closed?
The
When do you get this?
this guy, the intersection. And that's the
intersection.
So, right. Okay. So definition, now that we have this way of iterating derivatives, the rank of the lamination, or, again, more generally, this is a statement about topological spaces. The rank of a topological space is the point where the derivatives stabilize. Okay. So it's the smallest ordinal. Alpha, for which d alpha plus 1 of L equals d alpha of L. And again, if you're uncomfortable with this, just think positive integers here. Just think positive. So that's a little digression about this derived set iterated, which is sometimes called the Cantor-Benioff derivative. should,
Is it possible to start with lamination and then apply, and then it's not, if you apply dn times for n a finite number, it's non-empty, but then at omega you get something empty? You keep,
yeah, I think so, yeah. Yeah, I think that, this is what I'm after. That's what this, these are the kinds of things I'm after, so maybe we'll see, yeah. Oh, yeah, that is true, right, right. Because you start, yeah, yes, that's possible with an infinite time surface, yes. But, so let me just say, now back to the finite area setting. This is what got me started on this, so this is Casson and Blyler, but this is where I read it in their notes, because I think this is the first place that I think the notion of taking the derived set of a lamination appears. I'm not sure, I could be wrong about that. So they have this theorem. So if S is a closed surface, is a closed hyperbolic surface, then any lamination on S satisfies you don't have to go very far, up to the third derivative. Once you get to the third derivative, then you equal the second derivative. And in fact, this happens, yeah, so that's in general. And then if L has no closed leaves, which is possible, then in fact the second derivative of L equals the first derivative. Okay. And of course, if L is all closed leaves, then the derivative is empty. Everything's an isolated. So, in particular, when S is a closed hyperbolic surface, and more generally a finite area hyperbolic surface, the derivatives stabilize very fast. So the rank of L is at most 3. This is for S finite area.
Does this equation say that the rank is 3 or the rank is 2?
Which one? This one?
Yeah.
No, it doesn't say that because it could be that D2 equal D1. This is in general.
Or it's okay. The
Yeah,
rank is
but
at
then
most-
these are particular cases.
So, okay, so is the rank at most 3 or is it most 2?
Oh, I see what you're saying. Yeah, this can happen. So I guess it's 3. It's at most 3.
But on the left,
What did I do?
the smaller number is the rank.
Whoops, okay. All right. Up to successors.
So,
Yeah.
can you have infinitely many non-closed and isolated leads? Can you use that? On a closed surface.
Wait. I'm not sure. Maybe somebody knows.
Okay. Yeah, just-
That's certainly known. I just don't.
Uh-huh.
Yeah,
Yeah.
that's certainly known. Yeah, so infinitely many non-closed leaves on top, yeah.
and the complementary regions all have finite area, so they're just a polygon, and you kind of,
Right.
so you,
Those leaves on the hyperbolic.
Oh, I mean on a closed surface.
Close to it. Yeah. Yeah. So I want to focus on these guys. This result, that if you just have closed leaves, derivative is empty in the finite derivative case. So when you start thinking about infinite type surfaces, there's a subclass that you can talk about, and that's the ones where the leaves are all closed geodesics. That's one thing you can do. Okay. But there's something that happens for infinite type surfaces that doesn't happen for finite type surfaces. You could have a sequence of closed geodesics accumulating to an open geodesic on an infinite type surface. So, therefore, this definition makes sense, and I'm going to give you examples in a moment. So, so S is a hyperbolic surface. A lamination on S is said to be DCL lamination L on S is said to be DCL, and this stands for dense closed leaves. If the closed leaves of L are dense in L, so I'll write down what that means. DCL, if for any leaf gamma in L, there exist leaves, closed leaves, gamma N in L, so that the gamma N converge to gamma in the space of geodesic. So this is equivalent to saying, remember I gave that equivalent formulation of what convergence should mean at the surface level of the space of geodesics. It should be that there are lifts, gamma tilde and gamma n tilde, where this guy converges to this in the space of geodesics on H. This was equivalent to this. So this definition, well, it's a definition. Dense closed leaves. Okay. Well, it's not very interesting for finite type surfaces, finite topological type surfaces. Why? Well, so let me write down a little lemma before I show you why. But by the way, examples of DCL lamination as well, on a finite type surface, just take any disjoint union of simple closed geodesics. That's a DCL lamination. So just a quick lemma here, that the closed leaves in a DCL lamination are isolated in the DCL lamination. So the closed leaves, this is for any surface. So the closed leaves in a DCL lamination L are isolated. So what's the idea? Well, the idea is if the closed leaves weren't isolated, right, well, what could they converge to? Right? No, let me back up, I'm sorry. We have a DCL lamination. The leaves are either closed or open. Let me first throw out, if the leaves are open, so, yeah, so why are they isolated? Take a closed leaf in your DCL lamination. Okay. If it's not isolated, it's the limit of other leaves. Okay. Now, it can't be the limit of closed leaves, that would violate the color limit.
This is only for finite area.
No, this is in general. This is in general. It would violate the column. So the proof is, why are they isolated? Start with a closed leaf. If it's not isolated, two possibilities. Either it's the limit of other closed leaves, but that can't happen because that would violate the column law. Or it's the limit of open leaves. Okay? But if it's the limit of open leaves, well, this is a DCL lamination. Arbitrarily close to an open leaf is a closed leaf. So you can push down to a subsequence and then you can't be isolated. I'm sorry, you can't be the limit. A closed leaf can't be the limit of other leaves. So it has to be isolated. Okay, sorry, I butchered that, but that's correct. So, and that's for any infinite types, any hyperbolic surface. Okay? Now if we go to finite area, or finite topological type, if all the closed leaves are isolated, so using the lemma, if S has finite topological type, the DCL laminations are just unions of closed geodesics. Maybe you want to call this something else, a lemma or something, proposition, because it uses the lemma. Then DCL laminations are just finite unions. Of closed geodesics.
Yeah.
Don't be so agreeable, because we'll be here for another hour. Are just finite unions of closed. So the proof of this is, well, it's a DCL lamination. Leaves are either closed or open. Can you have an open leaf if S has a finite topological type? Well, if you have an open leaf, it's a DCL lamination, it's the limit of closed guys. Well, you can't have infinitely many closed guys on a finite topological type surface. They're all disjoint. You can't. Therefore, that leaf couldn't have been open, it had to be closed. But all the closed guys are isolated, therefore there's only finite many, and you can even give a bound in terms of genus. Okay, so so what's the upshot of this discussion? DCL laminations are not so interesting for finite type surfaces, finite topological type surfaces. Okay, and of course their derivative is empty right away. Okay, so that's what this whole excursion was about. So let me just state the theorem, which is for infinite type surfaces, this is these laminations, these DCL laminations are already a rich set of laminations. By the way, when I say a rich set, I mean in the sense of infinite type surfaces. So, in other words, there's always compactly supported laminations you could talk about, but then that's really like looking at finite type guys in the infinite type. So that's why this discussion is more about the guys that are not compactly supported. And these DCLs can be non-compactly supported in an infinite type surface. So the theorem is, so there's parts to this theorem, so I think what I'll do is I'll give you the corollary. Yeah, the corollary. So this is the corollary of the empty theorem, the theorem that was never stated. So one, for every countable ordinal, beta, there exists a DCL lamination. Implicit in all this is that these laminations are all on infinite type surfaces. I'm not going to write that. There exists a DCL lamination L, whose leaf space, so its topology is, first thing is scattered. That's a topological condition. I'll say what that is in a moment. Is a scattered set with rank of L equal to that ordinal. So this is already a different, so you don't like ordinals, just take any positive integer. Okay. Any positive integer can be realized as the rank of some DCL lamination. Okay. Scattered means that, so this is topological condition. Scattered means that every non-empty subset has isolated points in it. Okay. Another way of saying it is, if you keep, this is a count, if you keep taking the derivatives, the Cantor-Bennington derivatives, they'll eventually go to the empty set. That's what scattered means, if you like, for at least the countable set of points. So, so we have that. Then on the other side, we have for every countable ordinal.
So when this rank occurs, it's empty set equals empty set.
Yes. Or whatever, you know, up by one or by, yeah. For every countable ordinal beta, there exists an lamination L with all open units. So that, and rank. Valley to beta. Okay, so this is not DCL. It's very different than DCL, but you can imagine how to do it, right? Because I already told you. I mean, what do you do? Take one of these guys, where this is beta plus 1. Take the derivative. If you take the derivative, you throw out all the isolated points. You take out and throw out all the closed leaves, because this is a DCL lamination. Whoops, did I write? Yeah. So when you take the derivative of a DCL lamination, since all the closed leaves are isolated, you're throwing out all the closed leaves, you're left with open leaves. So you get 2 from 1. You get 2 from 1.
Is this on any infinite type surface? Or
Yeah, so that's a good question. Yeah, that's a very good question. So like I said, this is preliminary, so I haven't, so this is done on fluid surface.
Okay.
But fluid surfaces sit inside all other surfaces. All surfaces have, infinite type surfaces have a fluid surface in it. So I expect that it's all true for any infinite type surface. And then the third, and then I'll stop, sorry. There exists a DCL lamination. And this is on a fluid surface also. with Cantor Bendixson derivative of Cantor psi. And the idea, all of this goes through using, so the main tool is a generalization of the combination theorem for Fuchsian groups. A far, well, let's say that, a reaching generalization of the combination theorem for Fuchsian groups. You just keep putting together, in fact, pairs of pants that are represented by a Fuchsian group, and then if you do this right, you can construct such groups. Okay, thank you very much. I'm sorry.
So, are there any other questions? Okay. Here. first.
Okay,
Oh,
okay, in your number 3 in the corollary, can you found DCL-lamination with a DL whatever subset Cantor set?
as a what? Sorry.
Can you find DCL-lamination such that DL is a whatever subset Cantor set?
Oh, I
Can
see.
you find?
I see. Countable subset, maybe countable subset.
Okay.
I'm not sure, but countable subset. Yeah. Closed countable subset.
Yes. The lamination you built, are they maximal or not?
Are they maximal?
Yes.
So maximal means,
You
so
cannot have
maximal
any-
is what kind of lamination? A DCL lamination? Or
The one which you built in your experiments.
but are you asking, so what does maximal mean?
You cannot add any leaf and keeping it a lamination.
Okay, no, they're not maximal in that sense. No. I mean, the idea is, right, I'll give you a simple example. You start with a pair of pants. We want another pair of pants. We want another pair of pants. If you look at those geodesics that you're gluing along, they're nested. Okay? So this gives you, and if you do this so that this surface in the limit is, for example, not complete, so that it limits to something open, then there's an example of this sequence of closed guys converging to this open guy. Now you might have an issue with that not being complete, but then you can do other things for complete guys so that that limit does exist. But they're not maximal in the sense that you're just looking at these closed leaves, and so you could always stick in something that spirals. But you could ask for maximal DCL. That's, and that, yeah. Maximal DCL is sort of like a generalized pants decomposition. Yeah. Sorry.
So what happens if you take finite surfaces with punch?
Yeah, so then DCL laminate, same statement, because finite surface with punctures, I meant, that's finite topological type. So DCL are just finite unions of closed.
So Kassenleider also works for them? Or?
Sorry?
Kassenleider, the theorem of Kassenleider also works for them? Or?
Maybe you have to sort of like refine what you mean. Which theorem? The theorem about the derivative?
How often do you have to take the derivative?
Yeah, so I think you have to talk about the leaves that stay inside the compact part, maybe. Yeah, because it would shoot out. Right, so I'm not sure about the ones that shoot out.
Any more questions? No? Well, I do have. Is it by the way you glue pants that you get the fluid surface, or there is something special about the fluid surface that makes everything work?
It's just easy to work with. There isn't something special about the fluid surface. Yeah, I sort of expect all of this to work more generally for an infinite type surface. Yeah. And I mean, one reason to believe that is that every infinite type surface has sitting inside it as a subsurface, a fluid surface. Anything you want. Take an infinite genus guy that goes off, you can cut it open and you get this fluid.
Okay, then we can speak again.